So this is a joint work with my colleague Mario Sazzetti. So in this work, we study the problem of rearranging objects stored in stacks. In the basic setting, there are n stacks, each with capacity d. There are n types of items. Each type has d items, right? So these items are randomly scattered in the n stacks. There is also an empty stack to be used as buffer space. The goal is to minimize the total number of stack, pop, push operations to complete the sorting task, going from the left to the right, as you can see, right? So each pop push would operate on a single item. The problem may also be fully labeled. That is, each item can have a unique label. The problem finds applications at container shipping ports where containers may be, may need to be sorted, or sorting items at grocery stores and so on. Previously, we were able to get a lower bound of omega nd and an upper bound of O nd log n plus log d. In next slide, please. So in this work, we were able to narrow the gap between the upper and lower bounds, right? Via an intermediate result that we call the Rubik table. So in a Rubik table problem, let me just read the problem definition. Given an n times n square filled with n types of items of n each, in a shuffle, one may permute a single row or a single column arbitrarily. The question is, how many shuffles are needed for realizing an arbitrary reconfiguration? That is, sorting from the left to the right, right? Either by color or by label. Now, as it turns out, we can solve the Rubik table problem using only 2n shuffles if we do not care about the label, just only the color, and 3n shuffles if we want to sort by labels. Next slide, please. The Rubik table problem has many generalizations. So one of these here is the fat Rubik table problem, where we add one more dimension to the table in the back, right? So now each shuffle will not only work on a column or a row, but all the columns and rows behind that column or row. Now, with this update to the problem, then we actually have the same 2n, 3n shuffle results. Next slide, please. As you might have guessed, right, from here to solve the stack rearrangement problem, we will simulate fat column or row shuffles. We do this recursively to be, I guess, am I running out of time already, or?
Yep, I'm afraid that timer was already.
Okay, okay, all right. So let me try to be quick. So basically, we're kind of simulate these, right? So the goal is we start from an arbitrary n. We work with d equals to 1 square root of n and so on. Now, without getting into details, we can view the n stacks, right, as the set of square root of n fat columns and fat rows. In the example, n equals 16 and square root of n is 4. So the fat Rubik table result can be then applied. This gives us, for any constant m here, and the upper bound becomes O and D, which meets the lower bound. So next slide, please. So I'll just be quick with this, right? So there are some open questions. We don't know whether the problem itself is NP-hard, although we believe it is the case. And then we kind of narrowed the gap for most N and D, but there are still some of these gaps left. We're not sure how to deal with this. Can we get better lower bound? Can we get better upper bound? Thank you.
All right, thank you. That was a clever ploy. Run the clock down so you don't have time to discuss the dirty laundry. That's very clever. So Terry, do you have a quick question? Maybe we'll make it one question for JJ.
Okay, yeah, I just wondered, thanks for the insightful and creative presentation, but there seems to be something fundamental about the way humans solve this task, where they have multiple buffers instead of a single buffer. And I was wondering if there are any asymptotic complexity gains you can have from that.
Yeah, so we started briefly the question of multiple buffers, and as it turns out, as long as you have fixed number of buffers, it does not really help you when you are dealing with this n and d here, where n and d can be arbitrary. Only when you get to something like square root of n number of buffers, then certain things will change.
Cool, thanks. Let's move on to next presentation.
Hi. So I'm Nick Holland. I'm a PhD student at the University of Queensland, and this is some work I did with my advisor, Hannah. So a number of techniques for end-to-end learning and planning in systems with a priori unknown dynamics have recently been proposed. Among these techniques, there are a number of frequently occurring components. To enable learned models to generalize better using less data, we focus on improving one of these components, the forward propagation module, which propagates information on the basis of learned stochastic models with a state transition function. Next slide, please. LCI-Net, short for locally connected interrelated network, is a neural network module for forward propagation. It can be embedded in a variety of neural network structures and learns an expressive transition model which efficiently captures key environment features. Adding the LCI-Net module to existing architectures enables significant gains in performance with only minimal additional complexity. Next slide, please. LCI-Net learns a transition model conditioned on state S, action A, and relative state change delta S. A convolution network predicts transition probabilities for each combination of A and delta S using local features of S as input, while a novel neural network structure is used to propagate information over each time step in accordance with the learned transition model. Next slide, please. We evaluate LCI-Net by applying it to the recently developed end-to-end POMDP planner QMDP-Net and comparing against the original on a variety of environments, some including dynamic elements. Agents are trained on data sets of small environments before being evaluated on large environments. Adding LCI-Net results in generalization performance improving by a factor of up to 10. Next slide, please. Our results suggest that improving small, often used components in end-to-end learning architectures is a promising direction of inquiry. There are a number of dirty laundry items. Adding additional shift directions necessary for high-dimensional problems results in a large increased complexity over existing methods. This can be compensated for somewhat by manually selecting a smaller set of shift directions to be considered. Their performance is sensitive to exactly how these directions are selected, and this may be a non-trivial problem for more complex systems. Thank you. I can answer the questions now.
Perfect timing. Thanks. JJ?
Yes, interesting work. As we kind of know, right, neural networks generally try to remember things. Right? I guess one of the questions I have is, you're saying you're training on small environments. Right? How small the environments can be for your method to be still effective? That is, you have to still be representative, right? The small environment, so that you can make it work on larger environment.
Yeah,
I don't know whether you have some. Yeah.
A small environment training set, so it varies from one environment to one environment type to the next. But a typical example is we train on an environment of dimensions 10 by 10 and a data set of about 2,000 different randomly generated instances of this 10 by 10 environment, and then go and evaluate on environments which are more like the 100 by 100 or 200 by 200.
Okay, so in some sense, you need to use the same kind of distribution, right, for that to kind of work.
Yeah, so we want our training environment set to have a fairly representative distribution of all the possible bigger problems that could come up.
Okay, thank you. Are there any other questions?
Well, Nick, you talked about end-to-end learning, but I suppose this forward propagation primitive can also be used in the context of, sampling-based planner for exploration.
I believe so, yeah.
But you haven't tried it.
This reminds me of, sorry, Costa, so this reminds me of the MP-Net, right? I think it's somewhat similar to that, right?
Yep.
Yeah.
Okay.
Any more questions? All right, back to you, Dylan.
If there are other questions, we should take them. But
yeah.
All right, thank you. Let's move on to Danny's paper.
Hi, so I'm Golan. I will present this paper. Hi, so I'm Golan from Tel Aviv University. Today I want to present what we call the space-aware reconfiguration problem. It was a joint work with Dan Halperin, Mark Van Greveld, and Micha Sharir. And the problem, the original static problem, is if we're given two configurations S and T, each contains n non-overlapping unidisks in the plane, we want to find a collision-free itinerary where each disk moves exactly once along a straight segment from a source to a target. So each disk in S needs to move to some target in T. This is in the unlabeled version. Each disk can go to any target, and in the labeled version, the disks have labels. So each star disk have one unique target that he needs to go to. In the space-aware variant of the problem, we consider T as a non-static configuration, so we can rigidly translate it into somewhere else in the plane. So the new position of T, which we denote by T plus V, yields still a valid itinerary from S to the T plus V. And the space surrounds both configuration is minimized. Next slide, please. So this is an example of a valid itinerary. The left, the blue disks are the star disks and the orange disks are the target disks. And if you can click, this will be considered a valid move. And if the other disks will move as well, it will be considered a valid configuration, a valid itinerary, sorry. But another click. If we translate T rigidly into someplace else in the plane, maybe now there is a valid itinerary, but we're also interested in minimizing the space both configuration takes. So one click, maybe it will be the axis aligned bounding rectangle, or one click, smallest enclosing disk. And maybe it will be another place, another click. Yeah, just click like 3 times. Yeah, maybe it will be a better place and a better, more optimal axis aligned bounding rectangle or a smallest enclosing disk. More, next slide. Yeah. Okay, so about our results in the unlabeled version of the problem, we showed that the problem is always feasible. We can always find such a repositioning of T where we can we can find the valid itinerary. And we can find such a repositioning in order of n squared time. In the labeled version, we showed that some instances are infeasible. So no matter where we will move T in the plane, there will never be a valid itinerary. But if there are, we can find all possible such repositionings in order of n to the 6th time. And then we can also optimize for the axis aligned bounding rectangle or the smallest enclosing disk. And in the unlabeled version, wait, one back. Sorry. In the unlabeled version, we considered it a harder problem. So we just found a heuristic and we bounded that heuristic. And we even implemented it to show that it works well in practice. Next slide. What we can do, maybe consider other things to do is other rigid or non-rigid transformation of T, maybe different sizes of the disks in the labeled version. And we know that if we can apply a fully dynamic efficient algorithm for cycle detection in directed graphs, it can reduce our order of n to the 6th running time of our main algorithm. Thank you.
Thanks, Golan. Nick, do you have a question? In the meantime, I'll apologize for my poor clicking style. Sorry about that.
Thanks.
My bad.
So one question I wanted to ask, what sort of conditions on the start and target configurations for whether the problem is going to be feasible are there?
So we want just that at least one valid itinerary will exist when the disk will be able to move from their start configuration to the target configuration one by one without colliding with each other. It's not always possible.
Is it possible to tell in advance from looking at the start and target configurations? Like, is there's some intuition about what will make for one where a valid itinerary exists or not?
So one parameter that you can consider is how separated are the disks, and then it could tell you something. But mainly it takes about, in the labeled version, about n squared time to verify that. And in the unlabeled version, I think we think it's an NP-hard problem, but we did not prove it. Any other questions?
Any other questions? Yeah.
Can I ask a question? I was wondering if it's straightforward to extend to also account for obstacles, maybe spherical obstacles or circular obstacles.
I'm not so sure. Danny, do you have any idea?
Probably you can, but the cost will be much higher because behind this work is something that we call vipodromes, and you will have to elaborate them to account for the obstacles. So it will become a much more complex question with more entities to account for. But I believe it can be done.
I see. Thank you.
All right, thanks. Let's see. Yulin is our next speaker.
Hi, I'm Yulin. This paper is written with my provider Dylan Shell. Well, he's here, control the slides. So our work is about combinatorial filter minimization. Combinatorial filters are discrete structures used for estimation and inference tasks. They take sensor readings as input and output a sequence of colors. There's a notion of simulation from one filter to another. Filter minimization is to find the filter with the minimum number of states that simulate the original filter. Next slide, please. You may find filter minimization similar to automatic minimization, but they are different. So here we partition the set of strings according to the state they reach in the discrete structure. The strings outside the pi are the crash ones. For automatic minimization, which is shown above, you can never include a crash string to the partition that corresponds to accepting states. But for filter minimization, you are free to do that. You are free to include the crash strings to any partition you want. So this extra degree of freedom makes filter minimization substantially harder. So next slide, please. To minimize a filter, almost all existing work only consider merging operations to collapse states. But we show that it's not sufficient to just use merging operations. We should also consider splits. Next slide, please. So when the first filter minimization algorithm was proposed in ICRA, people were asking, does the minimizer yield a bi-simulation relation? Hashal and Jason have shown that it does not. In fact, here we prove a stronger statement. It's not even an equivalence relation. Next slide, please. In this paper, we introduce a notion of compatibility relationship that captures the set of states that can be merged. This leads to the first known complete algorithm. Here is the dirty laundry. Our algorithm requires an explicit representation of the compatibility relationship, which is exponential in size. As a consequence, our algorithm is not space efficient. Thank you.
Cool. So I guess Golan, you have a question?
Yeah. So if I understood correctly, you reduced the minimization filter problem into a click cover problem, right?
That's correct.
Yeah. So are the merges and splits that you described, are those procedures are part of the preprocessing of the graph, or are in relation to the clicks that you can achieve from the click cover solution?
Right. So this merging and splits are interpreted by these covers. So
okay.
In a partition, you can imagine each equivalence class is a merge operator. You're trying to merge the states belong to the equivalence class to a single one. But for a cover, one state could be covered in multiple groups. So in that case,
you have to
interpret that as right. You interpret that as a split.
Okay. Thank you.
Okay. Thanks, Yulan. Let's see, Andreas.
Yeah. Thank you, Dylan. So hello, everyone. My name is Andreas Ortei. I'm a postdoc with Marc Dusong at the Max Planck Institute in Germany. Our paper is titled Visualizing Local Minima in Multi-Robot Motion Planning using Multilevel Morse Theory. And the core problem we like to solve is to develop a new optimization algorithm, which not only finds a global optimal solution, but which can find all local minimal solutions. This is important because local minima can be used as symbolic representations, as analysis of trajectory optimizers, or as options for replanning. Next slide, please. This work extends and builds upon recent work on topological robotics, sparse roadmaps, multi-level abstractions, and multi-robot motion planning. Next slide, please. Our novel optimization algorithm uses sparse roadmaps to propose candidate trajectories, then uses an optimization algorithm to let the trajectories converge to local minimum, and we then use multi-level abstractions to organize local minima. Our algorithm uses this input to visualize all the local minima in a motion planning problem. Next slide, please. We have extensively evaluated this algorithm, not only on toy problems where you can, for example, go left or right, but also on challenging multi-robot planning problems, for example, where mobile manipulators have to pass a crossing, where multiple robot arms have to avoid each other, or where drones fly around a tree. Our algorithm currently has too many limitations. Next slide, please. So the limitations, first, we do not yet have convergence guarantees. And I'm currently collaborating with Florian Pokorny and Marc Dusong to solve this. And second, we often have problems finding local minima in or near narrow passages. And to overcome this, we recently published a paper called Section Patterns, Efficiently Solving Narrow Passage Problems in Multi-Level Motion Planning. Yeah, and in conclusion, multimodal optimization is a great way to not only visualize options and compute symbolic representations, but also to increase our understanding of the structure of high-dimensional state spaces. Thank you.
Great, thanks. Yulin, do you have a question?
Yes. So I have a question regarding the structure of this local minima tree. So so here this algorithm requires a user to input a fiber bundle, but once you are able to automate this, you could somehow have a control of this local minima tree. So my question is, have you thought about like the property of this, how the property of this local minima tree could help, for example, the design of this multi-robot planning problem?
Yeah, so to give a bit more context, so in higher dimensional spaces, you have oftentimes a very large number of local minima, and somehow we need to like create equivalence classes to like put them together. And currently, those equivalence classes, they are created manually. And to make this autonomously, so we are currently thinking about ways to do that, but we do not have yet good results on that. Yeah, but this is definitely a very interesting thing. We have to think about how to actually group local minima together so that we have like a more meaningful understanding of what we actually computed here.
Dylan, can I ask a question?
Yeah, I was going to say, please, I know my job as timekeeper is to kind of keep us moving, but please, everyone jump in if you have a question. This is what we're here for.
Yeah, so in multi-robot planning, we can define different cost functions, right? It could be something like max-span or the sum of the costs. Which one are you optimizing here, and does it matter for your work?
Yeah, so actually it matters a lot, of course. So in this work, we optimize the minimal length of paths. And yeah, what basically matters in our work is the cost function and also the optimizer which you use. And the interplay between them is actually yeah, mattering a lot of yeah, what kind of local minima we find, and also how good we converge to a local minimum. So this is definitely something to investigate further. Yeah,
good to know.
All right, thanks. Let's Raoul's paper's next. Raoul?
Thank you, Dylan. And yeah, thanks to all the organizers for this wonderful, like, kind of mini meet, right? So I'm Rahul Shom. I'm a postdoc working with Lydia Kavraki at Rice University. And this was work done when I was at Rutgers University with Daniel Nachimowicz and Kostas Bekris. So what we are studying here is the problem of asymptotic optimality for task and motion planning. So just a brief recap, task and motion planning can be typical instances of, say, manipulation, where you have to search over grasps and placements and compute motions between them. So what are the kind of algorithmic choices you should use to compute these motions and sample these grasps and placements in order to guarantee asymptotic optimality, or in other words, to guarantee that you find a solution as the number of iterations of your algorithm increases, which converges to the optimal cost. Next slide, please. So previously it was shown, particularly in WAFR 2016, that if you build roadmaps similar to PRM star, but with twice the connection radius that was prescribed by PRM star, for each motion planning part, which would be connect, say, a grasp to the next placement, you can achieve asymptotic optimality in the space of the entire problem, or the entire task and motion planning problem. And they also required these transition configurations, where you basically move from one orbit of motion to the next motion to be on smooth boundaries of the space. Because you can think of manipulation where the task necessitates contact, so you would have to interact with these boundaries of free space. So what we contribute is, we show the minimal conditions necessary to get this property, which relaxes some of the previously imposed assumptions. Next slide, please. So the first observation is it turns out that the minimum thing you need to do is kind of make sure you sample all of these transitions, right, that are available to you. And you keep growing this search tree over the space of transitions while ensuring that you keep connecting pairs of these transitions with asymptotically optimal roadmaps. Now, the key observation is just maintaining the asymptotic optimality similar to, say, PRM stars, so using whatever radius achieves the property in the specific planning domain of connecting to transitions, while ensuring such a high-level search tree seems to guarantee that the entire process converges, which relaxes the larger radius that was previously dictated. Next slide, please. And the other relaxation that we do is that these contact points where you have to make contact with, say, the object or with placement surfaces can be irregular boundary points of the boundary. And it seems that this assumption can also be relaxed and it does not affect your asymptotic optimality. Next slide, please. Yeah, the dirty laundry is, yeah, of course, there are a lot of kind of modeling choices that we have to stick to, which are typically standard in sampling-based motion planning, like assuming that you have these samplers available that are aware of these manifolds. And the assumption of roadmaps also restricts us to steering functions and kinematic domains for now. And we will also look at more interesting cost functions and in the future.
Thanks.
For any information, please feel free to get in touch with me or like our videos. Thank you.
Cool. Do we have a question or two? Anyone?
Yeah, Raoul, thank you very much. So I wanted to ask you about the relation of your work to motion primitives. So many people do the same kind of things like manipulation and rearrangement planning by learning primitives, something like, I don't know, picking, pushing, pulling, throwing, or shaking also. Would you say that your planner removes the need for such primitives, or do you think we could somehow integrate those primitives at some point in your planner, for example?
That's a very good point. So like, yeah, actually in the dirty laundry slide, right, the second point is the use of effective heuristics. So the way I look at such primitives is they are essentially a heuristic in this intractable search space. So if you have to search over all possible combinations and sequences of transitions and all possible motions between them, the basic search is going to be extremely inefficient unless we guide it. So these primitives and strategies to effectively connect between transitions and sample transitions are invaluable in practice.
Yeah, thank you.
Anyone else? I don't want to rush if there's a question. If not, Craig's next, I think. Yep.
Hi, everyone. I'm Craig. I'm going to be talking about our paper, Inferring Obstacles and Path Validity from Visibility-Constrained Demonstrations. And in this problem, we're looking at if you have a demonstration from an expert that's navigating to a goal while they're also learning about the environment. We want to infer possible environments and plan possibly safe paths in that environment. Next slide, please. So why is this hard? We have some previous work that infers constraints from globally optimal demonstrations, but when the expert is also learning about the environments, we require a totally different approach because there's no guarantees on optimality. And there's some assumptions there you can read through if you're interested. Yes, thank you. Next slide. No problem. So how do we do this? We first decompose the space into where the demonstrator learns. That's in figure 1. And then we find an obstacle in this configuration that is both consistent with the demonstration, which is the solid black lines, and also does not intersect with some novel path that we're trying to evaluate the safety of, which is the dashed black lines. Figure 3 shows 2 more examples, including 3b, where there is no obstacle that is both consistent with the demonstration and also does not intersect with the novel path. So we know the novel path here is certainly unsafe. And in figure 3c, we show a cloud of many possible obstacles that are consistent. Next slide, please. So how do we plan with this? One method is that we either generate many candidate paths, and we evaluate our method on each of them. And at runtime, we have a suite of possibly safe paths that we can execute. And number two, we can generate a cloud of possible obstacles and then plan a path that is intersects the least number of obstacles. Next slide, please. So in conclusion, we can either infer possible obstacles or plan novel paths in these visibility constraint demonstrations. Few limitations, we're only in 2D right now. Obstacle generation is somewhat poor. It scales poorly, I should say. And I'll just say, don't try to implement your own custom CSP solver, which I did and was quite painful. So thank you. Any questions?
Thanks.
Yeah, so really great work. I love this kind of principle of discovering obstacles through this kind of human interaction, right? So I was wondering whether, what are your thoughts are about, say, using this obstacle reconstruction primitive for a robot discovering a novel scene, right? So where instead of the human gathering information along the demonstration, it's you basically replace it with a robot maybe executing its own kind of policy or planning under uncertainty.
Yeah, and I think for either case with human or robots, there right now this work is kind of agnostic to which direction you would take it, because we do require some pretty stringent optimality assumptions with respect to what the demonstrator knows. Either case, you have to kind of consider how the demonstration is going to degrade for either the robot or the human, which is going to, of course, be different because we process information much differently between robots and humans. Actually, it might even be easier with robots because we have a sense of like how it's planning. Because we wrote the algorithm potentially, and so we might be able to infer more information there.
Anyone else? All right. If not, Christos, I think, is next.
Yeah, thank you. Hello, everyone. I am Christos Verginis. I'm a postdoc at UT Austin. And this is a work with my PhD advisor, Dimos Dimaragounas, and collaborator Lydia Kavraki. So we consider the kinodynamic motion planning problem for complex robots with uncertain dynamics, and we provide a new solution by combining sampling-based methods with feedback control. Next slide, please. So the dynamics we consider here are standard Lagrangian dynamics as shown here. And common kinodynamic algorithms, they try to build a roadmap, a safe roadmap as shown in the right, by sampling states and control inputs and by simulating forward the dynamic equations. This could be inefficient, computationally expensive, and of course, it might be problematic if the dynamics are uncertain. So standard algorithms, they propagate the uncertainty in order to deal with this, but this might lead to conservative solutions. Next slide, please. So to overcome these problems, we combine geometric-based sampling motion planning with feedback control. So we use feedback control in order in order for the system to track a desired trajectory shown here with QD, and take into account the dynamics and compensate for the dynamic uncertainty, which have been noted here by theta. So we actually design a controller U as a closed form function of the state, the desired trajectory, and an estimate of the uncertainty. And we are able to prove that the system will evolve around this trajectory within a funnel whose size depends on the uncertainty bounds here. It's denoted by this constant B. And by using this tool, we are able to do geometric sampling-based motion planning in an extended free space, which is defined by this constant B, without using the dynamics. So as shown in the picture here to the right, we can obtain a geometric path whose distance from the obstacles is at least equal, or at least B. And then this path can be converted to trajectory, for which we can use the developed controller. So essentially, we decouple the motion planner from the dynamics, which are taken care of by the design feedback control. Next slide, please. So the drawbacks here is that we need to know, we need to have an upper bound of the uncertainty dynamics in order to input that in the sampling based controller, the sampling based planner, sorry. And of course, tuning of parameters might be needed for the feedback controller in order to produce reasonable control inputs for the system. Thank you.
Okay,
Chris, so it's nice to talk.
We give you the first shot.
Okay. Yeah, I like this idea. It makes a lot of sense to have this feedback controller. I'm kind of curious, for designing this feedback controller, it seems like there would be some conditions you need on the dynamics to guarantee its existence and construction. I wonder if you have any insight or additional assumptions that are needed to do that.
So yeah, one condition of the dynamics, at this point for this work, they need to be holonomic dynamics. So for instance, this control design wouldn't work for a unicycle. And we need to have upper bounds on the uncertainty. So we're working, there's tons of like intelligence, you might say, feedback controllers out there. And we're actually trying to figure out if there's a way to integrate them.
Thank you.
Can I ask a question?
Please do, yeah.
I was just wondering, when you're decoupling like the motion planning step and the motion feedback controller step, you're assuming something about the reachable set of your closed loop feedback controller, right?
Yes.
I was wondering, do you compute this offline, or do you just assume that they're roughly at the sphere around your every time step?
Actually, by assuming that the dynamics are holonomic, then the system can track any trajectory that the geometric motion planner will give. So it's a condition actually saying essentially that the system can move in whatever direction.
I see. So it's the same as the last question, right? I agree. I see.
Yeah, exactly. Yeah. So we're working in order to tackle, take into account more complicated systems, like under actuation, like UAVs and unicycle dynamics that cannot move laterally, for instance.
Cool. Okay. Thanks, Christos.
Thank you.
So we have Eric next, I think.
Hi, can you hear me?
Yep, you're audible.
Okay, great. I can get started. Hi, my name is Eric Huang. This is my paper on efficient contact mode enumeration in 3D. This was work done with Xiangyi Cheng and Matt Mason at the Manipulation Lab in the Robotics Institute at Carnegie Mellon. This work was sponsored by NSF. Can you go next slide? Yes. So I believe contact modes are a useful tool for programming robots which have to make and break contact. I tend to think of manipulation in terms of manipulation primitives such as grasping, pulling, sliding, lifting, stuff like that. And contact modes are a programmatic way of describing and generating those primitives. Each contact mode maps to a smooth region of the dynamics. And ultimately, we want to use this information to help us sequence different primitives together to plan. Next slide, please. Can we play the video?
Give it a shot.
Yeah. Okay, this paper is mostly contributing to the theory and the computation of different contact modes. So on the left, we have a scene with a robot moving this block through all the different modes that it can be in. In the center, we have the hyperplane geometry described by the different contacts in the generalized velocity space. And on the right, we have a contact mode lattice, which is a highly structured combinatorial object describing how the different contact modes are related to each other, which I believe will be useful for planning and optimization in the future. Okay, go next slide.
Wait, is this the same one? Wait.
This is the same slide, yeah.
Okay, let me.
Our algorithm described in this paper is the first to enumerate contact modes in 3D. Previously, it was only possible in 2D. So in this video, we show, for instance, this box on a table in this particular configuration, all the different ways it can slide along the table. And if we move down the lattice, we'll be lifting and moving the box in different ways. Next slide, please. So I believe contact modes are useful for robots that have to make and break contact. Our work contributes to the theory and computation of contact modes. Some dirty laundry, contact modes are polynomial in the number of contacts and exponential in the degrees of freedom of the system. For an object that you're trying to manipulate, we can still enumerate them quite quickly, so that's okay. One other issue is that you need a numerically robust implementation to actually access these contact modes because the geometry can be degenerate in various ways. All right, I'm open for questions now.
Cool.
Nice talk, nice work. I was wondering if what exactly is the input to the algorithm? So I'm guessing geometrical characteristics, but do you also need friction parameters, for instance, in order to compute the contact mode?
For these contact modes, it's purely kinematic. Of course, they map to the dynamics, and then you need the friction parameters, but it's just the contacts and sort of a linearization of the normal velocity constraint or some tangential sliding direction constraints. So like the inputs are the contacts and like the normal vectors and tangent directions.
Okay, cool. And how, what is regarding complexity, what is the roughly the time it would take for like common manipulation tasks?
Okay, so for a single box, what we've gotten it down to is some of the more latest work in this paper. It's like less than a second, anywhere ranging from 10 milliseconds to 200, 500 milliseconds, depending on the complexity. The complexity of the enumeration is O(n) to the d over 2 for contacting separating modes, and O(n) to the d squared for sliding sticking modes. So n is the number of contacts, d is the effective degrees of freedom, which is actually less than the number of degrees of freedom of the object. So in practice, it can be done fairly quickly.
Okay, cool. Thank you.
All right. Anyone else? No. We'll move on. Thanks.
Okay. Hi, everybody. My name is Hazar Rahmani. Our paper is entitled Planning to Chronicle and is a joint work with me, Dylan Shell, and Jason O'Kane. We consider a problem in which a robot is tasked with autonomously recording a sequence of events in an uncertain environment to form a structured story. Imagine, for instance, a situation when we want a robot to make a video of a wedding reception or a nature documentary from a wildlife reserve. Next slide, please. We treat the problem via atomic elements called events. Each event is a letter from a finite alphabet, and we model the occurrence of event using an augmented hidden Markov model. The robot has no control or influence over the generation of events, but it does have control over what it chooses to record. If the robot anticipates the correct event and directs its sensor appropriately, it will successfully record the event. The robot's job is to collect a sequence of events that make a story, and we specify desirable stories using a deterministic finite automaton. Next slide, please. The robot uses a policy that at each time step based on the current belief state over the event model and the current state of the DFA chooses an event to try to capture in the next time step. The objective is to record a desired video as quickly as possible. In addition to the basic problem, you consider two extreme variants of it, in one of which the current state of the event model is always observable to the robot, and the other one, the current state is hidden. Our solution to this problem first makes a POMDP and then computes a policy that minimizes the expected number of steps to reach a goal belief state of this POMDP. We implement our algorithm on 2 case studies. Next slide, please. We also introduce several language mutators that are used for making specification DFAs in several interesting scenarios. An example of those scenarios is when we want a robot to make several videos for several recipients using a single execution. Next slide, please. So our approach has several disadvantages. It does not support low-level motion planning, and creating useful event model is challenging, and also the partial observability does not extend to recognition of events that might have been captured. This could be an interesting idea for future work. Thanks.
Cool. All right. Questions? Eric, maybe?
Yes. My first question is, you mentioned in the paper about handling different types of additional constraints, such as, they have some travel time for the robot, stuff like that. How might you augment your algorithm to handle those type of constraints?
Yeah, so far in our work, we don't consider any motion planning constraints. But we have other work we have submitted to DARS and actually was accepted. In that paper, the motion constraint was also considered. But here, no constraint. The purpose of here just to, in this paper, to choose appropriate standard structures to formulate the problem and also theoretical result and several language mutators. So basically, it introduces a problem.
And how might you handle certain DFAs which might be conflicting with each other? For instance, in your PalmDP, two events are happening, but they cannot, for two different people you're recording, but they happen simultaneously. What would the robot do in that scenario?
Yeah, the robot at each time step, it chooses only a single event to record because it has a sensor is capable of only one single event. So far, if even two events happen simultaneously in the same background, the robot considers only one of them to be recorded.
Okay, thanks. I think we better move on. Jehan?
Hi, everyone. Am I coming through?
Yep.
My name is Dion, and I'm going to just tell you a little bit about our work in maybe the space between filters and smoothing. Everyone will probably recognize there's a long-going discussion about when do you use a filter and when do you use a smoothing approach. And we're trying to maybe fill in a little bit in that space. And one of the key advantages in a filtering approach is that you can marginalize out old history. And the contribution that we'd like to try and make here is, can you do the same thing when you go to a tree structure? So next slide, please. So classically, in a filter, a Kalman filter or a particle filter, you basically build up a hidden Markov model. And in this example, you sort of add information growing towards the right, and you marginalize out old information. So this, whatever the state vector was at k-2, k-1, k, that gets you sort of ignore that. You don't work with that in your processing. And the sort of more familiar dynamics equation in probabilistic form, you transit from x2 to x3, and then you marginalize out the old x2. Now in SLAM, localization and mapping, EKF SLAM work this way. So the state vector becomes really big. The problem is all the interconnects, the joint density, the correlations between all the dimensions become dense and really difficult to sort of deal with. So in 2005, work showed that you don't have to do that. You can work sparsely. Next slide, please. So the idea of a Bayes tree, which is actually a WAFR paper by a co-author, Michael Case and Frank Gellert, showed that maybe we can sort of specialize junction trees in a certain way. So we take a structured approach to build the Bayes tree, and let's be specific. Let's maybe say the youngest variables, the newest variables coming into the problem should be at the very top of the tree. So all the history sort of hangs down on it. And then that's sort of a sequence of how you build the tree that's sort of understood and documented. Next slide, please. So our contribution here is to sort of describe how would you marginalize the history sort of hanging down in this tree. And it doesn't have to be at the bottom, it could be at the top too. And basically, we sort of feel that it's a Chapman-Kolmogorov transit equation is sort of the fundamental crux thing here. So you convert the problem into an acyclic tree, and then you calculate by propagating the leaf from the leaves up to the roots and then back down if you want to. But you can skip steps if you already have an answer. And each of these nodes in the tree is described by this Chapman-Kolmogorov integral. And the thing on the left there, the leaf over the theta s, which are the separator variables, the variables that sort of give the connection, that is a conventional belief propagation value that you send up. It's now just over a slightly higher dimension. So next slide, please. So this is the dirty laundry. We didn't say, how do you solve Chapman-Kolmogorov? Now, if you do it in a Gaussian sense, it's it becomes easier. That this Chapman-Kolmogorov equation reduces down to something like Cholesky factorization or QR factorization. For this work, we actually used a non-Gaussian solver that we've built, and we propagate multimodal non-Gaussian belief up and down on the tree, and we show how we can significantly save a lot of computation. So if a robot is exploring or if a loop closure happens, we've got a lot more control on how much work the computer is going to do, which gives us a lot of the benefits of filtering, more conventional filtering. Thank you.
Cool. Okay, thanks. Questions?
Yeah, I think one question is about the connection between sparsity of the estimator and your approach.
Mm-hmm.
I mean, because it is inferred that probably your approach works best for sparse rather than dense estimators.
Absolutely. So here's just an example tree shown right now. That's the statistical independence structure within the problem. And only in a sparse problem do you have these sort of branches. If it was a very dense problem, you just get one massive fat clique with all the variables densely connected in it. So each of these cliques are dense, and sparsity is super important. But the idea is, think of a robot in this room, and then it navigates out to the next room, right? This allows you to either not update the old room or forcefully say, I don't want to update the old room. The tree and the sparsity give you a sort of a good practice approach of how you can control that computation.
Thank you.
Okay, unless there are unless there are pressing questions, I'm going to move us on. Anyone? Okay, all right.
Thank you.
Thank you. And I think Ali's next.
I'll be presenting actually.
Oh.
Cool. So I'm Thomas Beretta, and I'm here to talk about a paper that Anna, Ali, and I collaborated on, along with our advisors, Todd Murphy, and our gracious would-be host, Stephen Laval. We are interested in the challenge of building capable yet minimalist microrobots subject to the strict constraints on sensing and actuation that exist at the microscale. We focus on the task of micromanipulation, that is, moving an object from some initial position to a desired one. We abstract this task to the problem of pushing a cart along an infinite corridor and onto a goal region. And then we analyze the information requirements of this task under different robot designs. Next slide, please. We draw inspiration from the behavior of biological microswimmers, which would show up on the video, who leverage their body morphology towards generating simple and predictable boundary interactions with the environment. To develop similarly simple interactions for microrobots, we abstracted several types of boundary interactions into different types of bounce rules. And then we analyzed their information requirements. We proved that relative rotations with respect to a previous heading require the least amount of information. And then these relative rotations can exhibit emergent triangular-like limit cycles whose stability properties we analyzed. Next slide, please.
Yeah, so, okay, there we go. I tried to go back and forward and it didn't do that. So at least it went forward. Sorry about that.
No worries. With the goal of exploiting this limit cycle behavior in mind, we produced several robot designs based on the action and sensor primitives shown above, such as translation, rotation, and odometry. Next slide, please. We developed modular designs of different complexities based on these primitives and compared them using an information space reachability analysis. We found that while some designs are always capable of solving the task, the success of more minimal designs can actually be sensitive to initial conditions. Next slide. Hope this one works. Great. Here's a short simulation of a swarm of microrobots using our most minimal design. Over time, we can see how the swarm makes progress at the task by taking advantage of their triangular limit cycle. Thus, we have proposed a formal analysis of information requirements of planar micromanipulation and shown how we can make minimal robot designs more capable by taking advantage of the emergent interactions between agent and environment. Next slide. And then for our dirty laundry slide, we regrettably admit that the real world is not in fact an infinitely long corridor. And additionally, it is unclear whether the approach described here would easily generalize to curved environments and non-convex geometries. And finally, we note that prior to taking this work out into the real world, it will be very important to consider the effect of inter-robot interactions, fluid effects, and noise on the approach. Thank you.
Thank you. Again, sorry about couldn't get your video to work there.
No worries.
Dion?
Yes. So thank you very much. So I work in navigation and guidance, and it's really difficult to find out where robots are. So I totally appreciate being able to navigate or being able to get the job done without knowing where you are. So that's definitely valuable. My question is there a space to at least look at the relative relationship between robots? Have you guys, you maybe want to comment if two robots know that they're close to each other or far away from each other? Is there any sort of easy value or sort of things to look or be sensitive about there?
There certainly could be. So we're basing this on what we refer to as the information space framework, which Stephen Duvall, and maybe Dylan or Jason worked on some time ago. And you can easily have primitives in that framework that account for something of that sort, like maybe it would be the strength of a magnetic field between two robots or something like that, a scalar value. And I'm certain that you could use that to design good algorithms for collective movement in minimal settings such as this one. We haven't looked into those specific types of sensors, but it seems like a promising avenue.
Thanks.
Leon, I like to characterize your question. I work in area X. It's great to see someone solving a problem without having to use stuff in area X. It's unusual to say it that way, but but recognizing that the problems are hard. So great. Let's move on. Thank you.
This is Kostya. I will speak about our joint work with State and Dmitry Shov and Emilio Frizzoli from Motional. Next slide, please. All right. So in our work, we're addressing the problem of finding an optimal path where the cost function is multi-valued. For example, consider the task of finding a path that is furthest away from obstacles and is shortest subject to item 1. Cost of an edge would then be a pair of real numbers, a, b, where a is the distance from the edge to the obstacles and b is the length of the edge. And costs would be combined by taking the minimum of the first coordinates and summing the second. Objectives of this sort appear naturally in the framework of minimal violation planning, for example, and represent hierarchical objectives pursued by autonomous vehicles, such as find the shortest path subject to clearance requirements. Classical algorithms like Dijkstra or A-star will in general fail in this case due to the failure of the Bellman optimality principle, since a subpath of an optimal path may be suboptimal. The main contribution of our work is a polynomial time algorithm for finding optimal paths in graphs weighted by such and similar cost structures. So the key theoretical ingredients here are the concept of a regular cost monoid, which abstracts the type of a cost structure which admits effective representation of optimal paths. Next slide, please. So you can consult our work to learn more about how failure of Bellman optimality principle affects single wavefront propagating algorithms, and how cost structures can be abstracted, and how the iterative algorithm I mentioned works. Thank you.
Questions, anyone? I feel like I was unnecessary there. Good thing the video played though, otherwise that would have been a tricky one, right?
Yeah, I've got a question ready here.
Great, that would be great.
So as I understand it, one of the core ideas of your manuscript concerns this shortest path planning in the multiple objective setting. But at least in my experience in robotic planning, often we tend to incorporate multiple sub-objectives into a single meta cost function that considers a bunch of different indices. So to say, I don't know, a quadratic cost that considers both a cost in the position of the robot, on the position of the robot, or maybe perhaps its actuation, right? And what do you think are the advantages of multidimensional objectives such as the ones that you consider here versus these compiled meta objectives?
So two things come to mind. One is algorithmic, that is, it's easier to separate concerns if they each cost represents a separate coordinate. So you avoid the necessity to concoct a function that isn't canonical in any way when you combine the costs. A completely different perspective comes from dealing with regulators. So a lot of these algorithms eyeing autonomous vehicles, applications for autonomous vehicles. And then when you explain to a regulator how your car will behave, if you tell them that you always make sure you satisfy clearance requirement, for instance, before you smoothie your path, they understand that. If you say that you have that much weight on smoothness versus clearance, that becomes trickier and raises more concerns.
Thank you. Excellent answer.
I have a question as well, if that's okay.
Yeah, jump in.
Yeah, so maybe this is a basic question because I'm not as familiar with multi-objective optimization, but what does it mean for a path to be optimal with respect to multiple objectives? Does it mean like you have a weighted sum of them, or there's like a constraint on one of the costs?
We consider lexicographical ordering. So you optimize the first constraint before moving to the second one. Since when you are talking about finding a path that is as far away from the obstacles as possible, in the example I gave, there would typically be many different paths that optimize this objective. So among those, you would like to find the shortest one.
Got it. So you're essentially sorting after you like breaking ties.
That's right.
Yeah.
Okay, thanks. Let's move on to the next one.
Hello, I'm Tom Tsaba. This is a joint work with Professor Dan Alperin and Dr. Efi Fogel. The work is about automatic generation of single-piece snapping fixtures that can be assembled from a separated state. We can see an orange fixture snaps onto a blue workpiece to the right. Next slide and play the video, please. Thanks. Let's see an example of a fixture snaps into a workpiece. Next slide, thanks. How is the fixture built? The shape of the fixture resembles the shape of a hand. It consists of a single palm and several fingers, which are connected to the palm. In the assembled state, the fixture holds the workpiece firmly. Next slide, please. And play, thanks. We also have a website, which we will publish soon, where you can upload your workpiece and get 3D printing instructions for the optimized fixture. You can see here the picking of a palm to be of a facet to be the palm facet. And next slide, thanks. In the paper, we present, we prove that 4 fingers are always sufficient and sometimes necessary. An efficient algorithm that generates optimized fixtures in often cubed time. Use cases including 3D printouts in nylon and sterling silver. Heavy theorem, Ganus of graphs, and more fun. A little bit about dirty laundry. Fixtures only resist linear forces. They might not resist angular forces. And there is no solution for sphere-like polyhedra or other complex shapes. Thanks.
Thanks, Tom. Questions?
Any questions?
Yeah, I have a quick question. So can you comment on what's special about fixtures that consist of finitely many fingers? Is that a metrical restriction or a topological restriction?
About the smaller number of fingers?
So what I mean is, if does a finger have to be a metric finger? So it's a polyhedra or parallelepiped, something like that, or it's a purely topological requirement?
Topologically, finger is 2 facets. One is a neighbor of the palm facet, and the other is a neighbor of this facet. But we also can actually build the finger as a geometrically figure. So we can actually 3D print it and grasp the polyhedron.
So the algorithm would optimize over all topological fingers?
Yes,
right?
yes.
Okay, and if you consider a fixture that is not topologically a sphere, like a torus, is it possible that you will need less area?
For actually torus or polyhedra-like torus.
Polyhedra-like torus.
Oh, so we actually had an example of a polyhedra-like torus, and we also try to minimize the number of fingers. We can use another optimization function afterwards that might be the number of the volume of the fixture or the best grip or something like that. But
Okay.
the first optimization function is the number of fingers.
All right, thank you.
Quick question: Is the sterling silver? Could this be used for rings to hold diamonds and stones like that?
Yes, we actually 3D printed an earring with the sterling silver. The diamond didn't come in a mail in time, so we 3D printed a plastic diamond, but it holds also really tiny stuff.
Great.
I'm sure she won't mind a 3D printed diamond. It'll be the same to her,
right? 3D, yeah, plastic diamond. Diamond shape.
All right, thanks.
Thank you very much.
Move on to the next. Jan, you're not audible if you're talking. Oh, maybe we have. Do we have someone from this? Sorry, I'm searching my list of participants here to try to see if we have someone. Anyone not affiliated with the paper want to give a 2-minute talk? No, okay. I will, I guess, move forward, and if they're able to come back, we can come back and revisit this talk. Selim, are you there?
Yep, I'm here.
Great.
All right.
Take it away.
Sure. Hello, everyone. Thank you all for being here, and thanks to Dylan and the organizers for this wonderful event. I'm Selim Engin, and today I'll present our work on active target localization using noisy relative measurements. And this is joint work with my advisor, Wolfgang Schneider. In the problems we study, we are given a function that measures localization uncertainty, and our goal is to dynamically compute next measurement locations for a mobile sensor, such that the uncertainty of the target location estimates is minimized. Here, we assume that the targets are static and there's no data association problem for the incoming signals from the targets. Next slide, please. We focus on two relative measurement models, bearing and range measurements. In bearing measurements, the sensor acquires noise directionality information, whereas in range measurements, the sensor receives distance observations. We model both bearing and range measurements to be the true value plus some zero mean Gaussian noise. Next slide, please. We measure the location uncertainty, localization uncertainty using what we call Bayesian histograms. These are 2D histograms where each bin corresponds to the probability of containing the target position. And as the sensor gets new measurements, we aggregate them using the Bayesian update rule. Next slide, please. We show that using top-down images of these histograms as input to a CNN-based actor network, we can compute next measurement locations to localize multiple targets in the environment. Here you see two examples for localizing two targets using bearing and range measurements on the left. And on the right, you see some examples showing our method in action to localize 8 targets, again using bearing and range measurements. We see that most of the time our method is able to generate trajectories that enable localizing the targets with good accuracy. However, there are some failure modes where the sensor needs to acquire many measurements from the same position. Next slide, please. In conclusion, in this paper, we presented a method to actively localize multiple targets using an image-based representation that encapsulates the estimation uncertainty. We also show that our method compares well against a couple of baselines used commonly in practice. Our dirty laundry includes several important assumptions. We first assume that the targets are mostly static and the self-localization of the sensor is perfect. And finally, we assume that there is no data association problem for the signals received from each target. And in future work, we plan to focus on the case where the targets are moving adversarially. For multiple adversarial targets, we also plan to explore coordination strategies among multiple tracking robots. finally, we would like to extend our method to more complex environments and 3D environments. And thank you all for your attention. I'm happy to answer any questions you might have.
Okay, does anyone have any questions?
Yeah, I had a question. Oh, sorry. I just wanted to quickly ask, you mentioned there was some failure modes. Like, is there like particular cases where like failure always happen? Or like, do you have any insight into why it would fail at times?
Yeah, that's a good question. So our underlying method is an RL algorithm, which relies on taking good observations. But I didn't mention, but our noise, the errors can be like up to 30 degrees of angles for bearing measurements, for example. And then when you have multiple of them, like leading to very different directions, then the sensor may need to acquire like many measurements from the same location. So right now it may need to take multiple measurements from the same location. So we are considering that as an occasional failure mode. But other than that, it's pretty reliable to accurately localize the targets.
Cool. Thank you.
Yeah, thank you.
Any other questions? Okay, if not, I'm a little behind where I need to be, so I'm going to move us forward. And I guess it's Grace.
Hey everybody, so my name is Grace McFassel. I wrote this paper with my advisor Dylan Schell, and I'll be discussing how to obtain every action-based sensor. So the question of how much a robot needs a sense, such as this robot here, which we want to reach a goal, is questions discussed a lot. So for example, is the lighthouse just as suitable as a GPS for reaching this goal? And how can we be sure that the sensors we're picking are both useful to us and well suited to the task at hand? This question goes back to work done by Donald Erdman and others in the early 90s. Next slide, please. So one approach to this question is Erdman's action-based sensors. These are based on progress measures, which provide a sort of distance metric towards a goal. This metric allows us to determine where certain actions make progress, which in turn defines partitions on the world to form a virtual sensor. Next slide, please. However, there exists more action-based sensors than those described by the originally proposed method. In this sense, the standing theory is incomplete. There exist previously undescribed action-based sensors, and that's interesting both in the sense of fully understanding the space of these sensors, but also in the sense that some of those missing sensors correspond to plans for which we previously had no definable action-based sensor. To obtain these sensors, we need to define a progress measure, something that not all plans have. We show that all plans for which no progress measure exists share a common feature. In such cases, the paths the agent might take through the world impose conflicting orderings on the world itself, which we call crossovers. So we devised an algorithm to identify and handle these crossovers that we call CLIP. Next slide, please. So CLIP uses a two-step process to obtain progress measures in these cases. It first locates them, and then it searches for all possible resolutions to them. This yields a family of plans as its output, each of which has its own progress measure, and through that we can obtain an action-based sensor. Next slide, please. So for a bit of dirty laundry, determining if a plan has a progress measure or not is something we can do pretty quickly, but enumerating all possible solutions for it is not. While we can do some initial pruning of the search space, it remains quite large, and that's something we're still working on. And if you'd like to know more, our video's number 9 in the playlist. And if you have any questions, I'd be willing to take them. So thank you.
Thanks. Questions?
Yep, I had one question. Thanks for the grateful initially first. I was wondering if your method can be modified to assess like the contribution of different sensor modalities. Like for manipulation tasks, for example, you might have some tactile sensors versus vision sensors. Do you think you can like evaluate the contribution of each of those modalities as well? This might be a little tangential to.
Good question. Thank you. I would believe so. So what we focus on here in particular is sort of the interplay between the kind of plans you'd like to execute or what you'd like an agent to do and how that impacts your sensing requirements itself. So one of the things you can do is, if you understand how your sensors interact and how that ends up impacting what you can identify in your world uniquely and distinguish from each other, then you can take the outcome from this and you sort of compare it to various sensor setups and sort of see what works, if that makes sense.
I see. Yeah, thanks a lot.
Okay, thanks. Let's move on. Saurabh?
Yes, can you hear me all right?
Yep.
Hello, everyone. I'm Saurav Agarwal with Srinivas Akela. In this paper, we develop approximation algorithms for the single robot line coverage problem, wherein the task is to find an efficient route for a robot to cover linear features. These linear features can be 1D line segments or curves. For example, in the figure on the left, we have a portion of the UNC Charlotte road network, and the road segments form the linear features. In the middle, we have a route generated by our algorithm. Finally, we have an orthomosaic generated from the images collected by flying a drone along this route. Next slide, please. We model the problem as a graph. We have two sets of edges. First is the required set of edges, which correspond to the linear features to be inspected. We also have non-required edges that the robot can use for faster travel between the vertices. Next slide, please. We have two modes of travel. A robot is servicing an edge when task-specific actions, such as taking images, are performed along the edge. Else we say the robot is deadheading. Cost of servicing is considered higher than deadheading because of task-specific actions. Next slide, please. Here we have an example of a flight plan. The solid blue lines represent servicing, while the dashed green lines represent deadheading. You'll notice that the drone travels faster while deadheading, as it is not taking images and need not worry about motion blur. The costs are considered to be asymmetric on the edges, and here we simulate a wind of 2 meters per second from southwest. Next slide, please. In this work, we do not consider energy constraints, and we assume that the costs are known constants. In future, we plan to incorporate turning cost and non-holonomic constraints and also extend to multiple robots. Thank you.
Thanks, Saurav. Do we have some questions?
Yeah, I have a question. So first, thank you very much for your presentation. I was wondering if you could say a bit more about sort of how the problem's constructed and its scale and things like that. The example here seems to cover a pretty large road network, but do your edges correspond to like similar sized lengths of a road, or do you have, can you compress like large roads into a single edge and smaller roads into a single edge? How does that work exactly?
So in this particular example, we obtain the road network from, let's say, Google Maps or OpenStreetMap, and then each of the road segments are considered to be a linear feature that we need to inspect. And based on the sensor field of view, we could connect consecutive line segments into a single polyline or a single, let's say, a 1D curve. And that would then form our linear features and the edges in the graph. And thereafter, we need to assign some cost function, which could be like travel time. And we could have different costs for the deadheading, wherein you're not performing the task, and a different cost for servicing. And also we would consider if we have asymmetric edges, for example, the terrain might have hills, or we are considering wind in the environment for UAVs, then we can have asymmetric costs on the edges as well. And the formulation can handle all these different kind of scenarios into the framework.
Thank you.
Thank you.
Thanks. Okay, let's see. Alexandra, I guess.
No, it's Niels speaking today.
Hi, Niels.
Yeah, hi. Hi, I'm Niels, and I want to briefly present you our paper, Learning Control Sets for Lattice Planners from User Preferences. Let's jump in. Next slide, please. So we studied the problem of designing a motion planner that represents user preferences, for instance, a driving style of an autonomous vehicle. We consider a lattice planner where the configuration space is discretized in a regularly repeating grid. And these discrete states are then connected with pre-computed measure primitives. By concatenating these primitives, we can find a path from the start to goal configuration as shown in the figure over here. Moreover, the trajectories that are taken by the measure primitives should reflect the user preferences. Designing such a planner consists of two subproblems. First, computing user optimal trajectories, and second, choosing which connections, that is, which measure primitives the planner is allowed to use. Next slide, please. The first subproblem assumes a user model where a linear cost function trades off trajectory features, for instance, travel time and comfort. And we can estimate such a cost function from demonstrations. When we are using a lattice planner, we want to limit the number of connections to ensure computational efficiency. Thus, in the second problem, we select a subset of all possible connections that minimizes the worst case error when concatenating motion primitives compared to using a direct trajectory. Next slide, please. In our work, we proved that an optimal lattice planner is found by applying a separation principle. First, we estimate the user cost function. Then we compute trajectories that are optimal with respect to that estimate for all connections in the lattice. And finally, we select an optimal subset of connections given some budget. Next slide. In our work, we demonstrated in simulations that the designed motion planners can replicate user preferences and achieve a substantial improvement in worst case error and runtime. Our dirty laundry includes practical evaluation with real user data, as well as using more sophisticated trajectory planners. And finally, we want to extend the work using situational awareness with adaptive lattices. Oh, that's it.
Thanks.
I have a quick question. Thank you for the talk. How does the resolution of discretization affect the computation time and the quality of the results?
The resolution.
So as in how fine you discretize the environment?
It's like as soon as you get a fine discretization, you gain a lot in like fidelity of the paths because you have like more options to move around. But at the same time, it depends on like the budget that you set for your lattice. If you still set the budget small, it doesn't affect the computation time that much. It's just like you search over a large environment, but the branching factor of your planner is still defined by the budget, so it's not related to the resolution of the lattice. Did that answer the question?
Yes, thank you.
Niels, perhaps for higher dynamical systems where you may not be able to connect two states, do you think that some of the principles can still apply on learning preferable controls?
The main principle should still apply, and like the benefit of a budget on a lattice planner should still work out, and you should still get the same guarantee. You will get the same guarantee that first estimating and then computing the lattice is the optimal way of constructing such a lattice. The question is like how well does it perform like in a high dimensional case. So we tested it in a 4-dimensional case with position X, Y, heading, and speed, and it was a fairly good performance, but like with manipulator you easily get like into higher states.
Yeah, one question also, how do you generate the basically the demos that you solicit user preferences on? Like, are they generated of like, do you have like an idea of like a potential user cost function ahead of time and create different demos along that spectrum?
There's like pre-designed archetypes of users. Like one is very aggressive, they don't care about comfort, they just want to get to the goal quickly. And then we just set like the weights trading off comfort and speed accordingly. And then we generated like an optimal trajectory using that pre-designed user. And then we try to learn that. And similarly, like the other extreme is like a very cautious user that just wants to drive very comfortably and not have any jerk, like at least the minimum amount of jerk possible.
All right, thanks very much. Let's I guess Raul, you're back up again.
Thanks, Dylan. So yeah, hi everyone again. I'm Rahul Shom, and this was worked on with Professor Kostas Bekris at Rutgers University. And the problem here, you see this kind of army of what looks like squiggly arms moving in a scene, right? So it's a problem of object rearrangement. So what happens when you have multiple manipulators available to you to affect the change of object poses from the initial locations to a set of target locations? And the objective here is to quickly identify a sequence of picks, placements, and handoff actions that involve potentially all of these manipulators, and where you have to reason about all of them at the same time and their coordinated actions. So in this work, we want to identify efficient ways to find these candidate solutions to guide our search. Next slide, please. So the efficient structure we identify is what we call a mode graph. So this is kind of a graph built with information about the workspace. So it turns out that if you consider a graph with nodes being manipulators and placement regions being the locations where these objects can occupy poses, the edges between these vertices can express the actions that we have kind of narrowed down. So the edges between the placement locations and the manipulators are picks and placements, and the edges between manipulators are going to be handoffs. Now the objects can be thought of as pebbles on such a graph, and the initial location will occupy a set of vertices on such a mode graph. Next slide, please. So it turns out that if we solve the problem of multi-agent pathfinding for these pebbles over the graph, that can give a candidate sequence of actions, which if successful will give you the solution to the entire problem. And we have from previous work by JJ, in fact, which showed that there are very efficient mixed integer linear programs for these problems. And we use this in a high-level task and motion planning search to guide our solution for effectively finding these multi-arm rearrangement solutions. Next slide, please. So yeah, like this is just one of our benchmarks where we kind of demonstrated that if you try to solve this naively, right? So if you try to be greedy for each object's kind of solution, or if you sequentially execute these solutions, in which case you lose the benefits of having all of these arms available to you, you would have trade-offs. So we show that our method actually has a very high success ratio, which is similar to where you don't have to coordinate all these solutions together, and it will have a much better solution quality than if you had to do it sequentially. Next slide, please. Now, of course, just to kind of study this problem, right, and come up with these insights, we had to impose some structure to the problem. So the assumptions include that we only look at synchronized execution. And right now, all the experiments are for mobile manipulators, and we believe that there exists such a structure for when you have mobile manipulators, but right now it's only stationary ones. And we want to extend this to richer kind of actions as well. And here you can see kind of a very non-monotone problem where the objects has to be interacted with more than once that can be solved right now.
Thanks, Raul. Question? Nils, maybe?
Yeah, I have a few questions. The first is, in your paper, you have this one condition that is object non-interactivity, so that you don't have to cross behind, or like that you don't have to move an object to be able to cross another one.
Mm-hmm.
So as you say that this is like a condition that you need for your current framework, but I was wondering, could this current framework be extended to not depend on that, so that you could kind of weaken that assumption?
So that's a very good question, right? So that's kind of needed to ensure that the edges on the graph that we are considering are kind of independent, right? So the condition kind of naturally expresses the typical constraints you encounter in tabletop scenes. So instead of explicitly saying that we need the problems to be tabletop, the guarantee we need is that the transfer of an object does not necessarily need to care about where the other objects are.
Yeah.
So just to make it more efficient, we need this structure to exist so that the mode graph analogy is feasible.
So it won't be easy to construct a mode graph without that assumption, or maybe not possible at all, I guess.
Yeah, it might end up that the solutions would be infeasible even if you just consider the objects themselves, not even considering the motions of these arms.
Okay.
All right, thanks. I'm gonna rush us on a little bit. We're a little behind. Thanks, Raul.
Thank
Navi,
you.
you're next.
Hi, everyone. This work was done in collaboration with Dr. Chakravarti and Dr. Shell. So here we consider the problem of robotic planning and control in continuous action and state spaces under noise, which can be classically framed as a stochastic optimal control problem in the space of feedback policies. The solution to this problem is for nonlinear systems involves dynamic programming, which is computationally intractable. Next slide, please. In this work, we introduce, it's basically a position paper where we investigate two classes of tractable solutions, namely model predictive control and linear perturbation feedback. So both these solutions, which we show are near optimal, do not exactly solve the problem, but we show how near optimal they are. And we also show some experiments to prove our claims. Next slide, please. So as we have shown here, the near optimality of the perturbation feedback law can be shown using this decoupling principle, which basically states that the expectation of cost to go function is determined by the nominal trajectory, and the variance of the cost to go function is determined by the linear feedback. So the implication of this is the feedback law design can be decoupled into an open loop problem and a closed loop problem. We also show that the near optimality of MPC, which is basically the deterministic feedback law, is order of epsilon to the power 4, where epsilon is just a parameter which indicates the intensity of the noise level. So for small epsilons, the optimality of perturbation feedback and MPC is close to the stochastic feedback law. So next slide, please. So the experiments also show the near optimal nature, and basically when noise is low in low epsilon values, there's no difference between the deterministic feedback law, which is MPC, and the linear feedback law. But in high noise cases, we need the replanning and MPC to maintain our optimality. So as shown here, in low noise cases, MPC basically uses a lot of computational resources by replanning at every time step, as opposed to the linear feedback law, which replans only at necessary steps. So the optimality of the linear feedback can be guaranteed if we replan at specific instances rather than at replanning at every time step as seen in MPC. So we answered a couple of questions here. The one that we answered is, when is replanning actually needed, and in which regime is it needed? And the perturbation feedback law, which is thought to be a heuristic traditionally, is actually near optimal to the second order of the noise level, and can handle basically fair amount of noise by selectively replanning. So next slide, please. We also show the same trends in multi-agent setting, but there's a question of when and how to replan in a distributed fashion. Also, the decoupling law is applicable only for when the nominal trajectory is smooth and fails in systems such as legged robots where the trajectories are non-smooth. Also, the nominal trajectory could be a local solution since it's a nonlinear problem. But in our recent work, we show that for a large class of robotic problems, this is actually a unique solution, which is the globally optimal solution. Thanks.
All right, questions?
Yeah, really great work. And yeah, I have a quick question. So in the paper, you have this very nice figure of the amount of time you spend in each step, right? Which typically is very low when you're not replanning, but when you're replanning, it kind of spikes, which is different from what you would do in MPC, where you always kind of have this cost at each step. So do you have any thoughts on whether you can amortize the cost of those spikes so that basically like you don't have to give a huge amount of kind of time allotment to each step at the worst case?
Yes, so in practical scenarios, traditionally MPC is solved for a short horizon rather than for the entirety of the horizon. But as we see in experiments, the solving for a short horizon actually produces a very suboptimal solution. But to implement in a high frequency control setting, that short horizon assumption has to be held. But if we were to solve the full-blown optimal control problem, we have to solve for the finite time, the full finite time, which is computationally expensive. That's when linear feedback approaches come into the picture, which can make it computationally easy to solve those problems. But it is near optimal. And it can also, as seen in the paper, it can handle pretty large amounts of noise.
Raul, if you can solve that problem, I'd be interested to hear.
Okay, got it. Thanks for the great answer.
All right, let's move on to the next talk. Thanks, Naveed. So let's see, is it Ian? Is it Alexander?
It's Ali.
Okay, right.
So I'll be presenting this work today, done in collaboration with Ian and Alexander, Brenna and Todd at Northwestern. So we know that humans can learn from a very limited amount of experience. So that was the motivation for this project, was can we use experience-based learning with model-based reasoning to learn about the world more efficiently? So maybe one model will know about some obstacles and another will know about the task. Can we combine them optimally to learn better about the world? Next slide, please. So we approach this as a hybrid control problem, which more specifically mode scheduling. So can we figure out and optimize the reward to switch between these two policies where the mu is the model-based and a hat is the model, mu is the model-free and a hat is the model-based policy. And then to actually implement this, we can solve for control A star, which improves the reward at any time step. And so that first term in the equation encodes the model-based planning information, while the second ensures that we stay close to the model-free policy when it in fact has high confidence. Next slide, please. So if you look at how this works in implementation, so on the left, you can see in simulation, the model-free version just never gains enough experience to run. It constantly falls over. While on the far right, the model-based version, it initially start running, but then it falls and is unable to recover. But then in the middle with the hybrid learning approach, you can see that by combining the two tasks, it can explore enough to learn how to get back up and run. And it can also benefit from the initial model-based method that lets it run. Next slide, please. We also implemented a version on the real robot. This is specifically showing behavior cloning, where behavior cloning is used to construct the predictive model and to update the policy. And so you can see on the right that behavior cloning is, on the left, that behavior cloning is not always successful. Sometimes it knocks the block over, it suffers from the typical problems of behavior cloning, but by bootstrapping it with these expert demonstrations, it's able to learn and improve the model-based learning and more successfully repeatedly complete the task with hybrid learning. Next slide. So finally, dirty laundry, this is a gradient-based solution. So there is fine-tuning that's required, and exploration is still done through random sampling, and it's RL, so we can't necessarily verify the correctness. And finally, it doesn't necessarily improve learning, it just takes the features from both the model-based and model-free versions and optimally combines them. So if either of your models are bad to begin with, it'll still be bad when you do hybrid learning. It can only combine them in a way that becomes more useful. And that's pretty much it. I'll take any questions.
Thank you.
Hi, Ali. So I have a question. So do you, in your paper, you have shown two versions of the algorithm, the deterministic and the stochastic versions of the algorithm. So do you see a significant performance gain in modeling the problem as a stochastic problem as opposed to a deterministic problem?
We don't really see a gain. It's more just we're trying to show the breadth of the algorithm and how you can really attack different problems, because a deterministic is not going to always be appropriate for learning different tasks, especially with learning motor movements dynamics. So that's why we extended it to the stochastic version. Not that it's necessarily better, but that it allows you to solve more tasks.
Thank you.
On your first bullet point, Ellie, you're reminding me of something I heard at last WAFR, where someone said this is a grad-based solution requiring fine-tuning. By grad, they mean grad student required fine-tuning. So thanks. Let's move on to the next. Great.
Hello, my name is Karen, and I'm going to be presenting this work that I did in collaboration with Toyota Research Institute and my lab, of course. So providing structure into a robot learning task can help performance, both in terms of the training process and how it performs during deployment. And one way to incorporate structure is to use temporal logic, which is a formalism or language that allows one to describe spatial temporal properties. And it also provides a very nice and concise way to translate kind of rules or specifications from natural language into a concise mathematical representation. And so in this work, we build a computational paradigm that allows one to connect temporal logics with gradient-based methods, which are kind of ubiquitous throughout many robotic applications, such as deep learning. Next slide, please. In particular, we focus on signal temporal logic, or STL. And the main reason is because STL allows one to measure this notion, or is equipped with this notion of robustness, which allows us to measure just how much a signal satisfies or violates an STL specification. And so in this really simple example on the right here, suppose we have an STL specification that says the vehicle should always stay below the speed limit. And then for the speed profile at the bottom, I mean, we can just say, yes, this is true, right? It's always below the speed limit. But robustness allows us to quantify exactly just how much it is below the speed limit, and kind of denoted by that little arrow there. Next slide, please. In fact, there are these quantitative semantics shown on the left that tell us exactly how to compute the robustness value for any STL specification. But if you take a closer look, it's actually, these formulas are defined recursively. And so it actually gets nasty very quickly because it is made up of all these nested max and mins. And what we do in this work is develop a technique called STLCG, which allows us to translate these quantitative semantics into a computation graph, meaning we can then backpropagate through this graph and easily obtain gradients. And the really nice thing about this is that we can leverage highly optimized auto differentiation tools that are readily available to us thanks to the deep learning community. And in this work, I have kind of implemented STLCG in PyTorch, and you can find it in our GitHub shown on the top right-hand corner. Next slide, please. And in the paper, we provide a few illustrative examples to demonstrate how STLCG can be used in a variety of gradient-based methods, which I won't go into here. But I just want to point out that we're really excited about STLCG because it essentially provides a very nice and simple way to essentially embed logical structure into gradient-based methods. In particular, the thing that I'm most excited about is embedding temporal logics into neural network architectures. And this can, as you can see on this slide, provide some benefits such as allow a provide a mechanism for a neural network to potentially make complex decision-making involving spatial temporal properties. It also allows one to maybe encode human domain knowledge, like rules of the road, into a neural network model. And it also provides a lens for which to interpret a neural network. Next slide, please. And then, so yeah, in terms of my dirty but cute laundry, I guess a drawback or kind of like a implementation detail is that the computation graph is very similar to an RNN. And so this means that it can actually, the computation will take longer the longer your rollout is, and this can slow down your training time. Another thing is that, as you saw in the formulas, the quantitative semantics, the robustness formulas are extremely nonlinear. They're made up of a bunch of max and mins. And so this can make the optimization landscape very challenging. There are certain things you can do, like smoothing out or using soft min or soft max. And this can help with the gradients, but this can essentially still make the optimization more challenging. And then another detail is that in order to evaluate the robustness, you actually need the entire signal, the entire time series. But sometimes you don't have access to that, right? So you might have to combine this, say, with a prediction model that will predict what the future trajectory looks like given the past trajectory. And with that, I'm happy to answer any questions.
Okay, we need to take a quick question here.
A quick question is just, when you compose a bunch of these different logical structures together, is there an upper limit on what you can really process? Does it become intractable at a certain point? And are all of these constraints created equal? Or are some easier than others?
Yeah, so the more complicated the specification is, like the more complex your robustness formula is. And so kind of just working with that can become challenging, or optimizing that over challenging. But there really isn't an upper limit. Like I could make a super, super complex specification if I wanted to, but maybe there's no good reason to really do that in the first place if we want it to be interpretable.
Okay, thanks very much.
Thank you.
All right, now.
So today we will be presenting ABC LMPC.
Go ahead.
Okay, sorry. Today we'll be presenting ABC LMPC, safe sample-based learning MPC for stochastic nonlinear systems with adjustable boundary conditions. This work is in collaboration with researchers from UC Berkeley and Caltech. In this work, we'll discuss the following question: how do we safely explore the state space to learn goal condition policies in a stochastic nonlinear dynamical system? Next slide, please. Thank you. We first define a safe set in the state space based on regions visited by prior safe policies, which we use to construct improved new policies that are also safe. We prove guarantees for constraint satisfaction, convergence to the goal set, and iterative improvement for the sequence of policies generated by the algorithm. First, we focus on the fixed start, fixed goal set case. Next slide, please.
Yeah, then we generalize to variable start states, noting that the safe set can be used from novel start states as long as they're sufficiently close to it. And we present a procedure here to adaptively find such states and also iteratively bring the agent closer to starting from a desired starting state. And this is inspired by algorithms in safe and robust motion planning, and this procedure also maintains the same safety guarantees. Next slide, please. We then present a procedure to adapt the safe set to novel goal sets using a procedure similar to work in like hindsight experience replay and other goal relabeling techniques in RL. The safe set is retrained then on the prefixes of trajectories that intersect with the new goal set. And this again preserves the same guarantees as long as the new goal set is robust, control invariant. Next slide, please. And the theoretically desirable algorithm, one dirty laundry here is that the theoretical desirable algorithm involves solving an optimization problem, which is pretty difficult to solve exactly in complex systems. So we present a practical algorithm that approximates these properties. However, one issue is that the model-based optimization that we do with our approximation algorithm is fairly expensive and imperfect. So addressing these issues would be a cool area of future research that we'd love to discuss with anyone who's interested. So please shoot us an email with any questions or ideas you might have. And thanks for listening, and we'd be happy to take any questions.
Thanks. Questions?
Yeah, so I have a question. So in your work, you were looking at the like kind of reach avoid type problems, or at least the obstacles were like static. I was just curious, how could this extend to cases where you have, say, spatial temporal constraints where the obstacles, say, were moving or time varying?
Right, yeah. So it definitely could. It would introduce a new bit of complexity to the problem where we would have to model, say, value at a given time. So right now, everything is sort of Markovian. So we'd want to consider, I mean, I guess the trivial way to do this is to consider time as part of the state, but then that adds like complexity to the problem because now you can't share data across time. So I think that's where the core challenge is. We could model time, but the challenge is now we need to figure out a way to share data across time because we're kind of treating every time as separate. So that's definitely an interesting extension.
Cool, thank you.
Can I ask a question too?
Yes.
Yep.
I was wondering, what is like an assumption on your dynamics that would allow you to grow your safe set iteratively, like incrementally? Because if you're not stabilizable in some part of your state space, then you cannot do this anymore, right?
Yeah, so the assumption we make, it seems pretty broad, but the it's really coming from the fact that we assume the ability to have some initial controller that is safe and task satisfying robustly. So as long as you're able to do that, this algorithm can iteratively improve. Now, there are plenty of systems and plenty of tasks where that is not possible. And so that's really where this dynamics assumption is. Like the core assumption we're making, we're just saying that it has to be stochastic and nonlinear and like according to some format that we know. But the real dynamics assumption comes from the fact that you're like initially able to do the task, where there exists some like feasible policy that can robustly do the task. And so that's sort of up to the system and task.
Can I follow up? And the ideas are beautiful here, but I think you said you're safe as long as you're close enough to previous trajectory. So a notion of distance here is important.
Yeah, so that's definitely true. So in the theoretically motivated algorithm, it's not motivated by distance. It's actually using like reachable sets, robust reachable sets of policies. And so each trajectory is really like a sequence of reachable sets. And so as long as you're inside this reachable set, you are safe because you can robustly stay within the sequence of reachable sets. Now, when we do the practical algorithm, we don't like have these exact robust reachable sets. We have like actual points. And so we have to use a notion of distance. And so that's where this gets very challenging because oftentimes the distance metrics that we ended up using in low dimensions is like Euclidean. And that's not necessarily the most natural notion of distance between states. And so we do have some follow-up work where we have a latent space, where we like learn a latent space safe set and latent space obstacle, which seems to work better from image-based like control tasks. But in this work, we use the Euclidean distance, and that's not necessarily appropriate for more complex systems.
Great, thanks.
Okay, we're on to our penultimate paper now.
Hi, can you hear me?
Yes.
Awesome. I'm Chase Q. I'm with robotics at Google, and I'll be presenting a neural collision clearance estimator for batched motion planning. So the problem we're trying to solve here is that collision checks are slow, and in sampling-based motion planning, we need to do a lot of them. In fact, up to 90% of planning time can be spent doing the collision checking. What's especially galling about this is that most of the collision checks are not all that important in the grand scheme of things. In this image here of an RRT, at the end of the day, we extract this black path from start to goal. We care a whole lot about collisions that occur on the path and not so much about collisions in the rest of the environment. So in this work, we trade off speed for accuracy. We introduce a fast heuristic collision detector, which is not 100% accurate, but it's easy to verify the paths that it generates. Next slide, please. This is our heuristic collision detector. It's a neural network. We call it ClearanceNet. The input to the network is the state of the robot and the configuration of the workspace, of anything that can move in the environment. So in this case, the shelves can move and the cubes can move. And then the output of ClearanceNet is the minimum clearance between the robot and the environment. So we use this as the collision detector in an RRT, make a couple of modifications, including a neat trick with the gradient of ClearanceNet that we use to move the path more into free space. You can learn more about it in our video. Next slide, please. Once we have a candidate path, we want to make sure that it's actually collision-free, that there haven't been any mistakes made. So we check each point along our candidate path using a ground truth collision detector. In this middle picture here, the red segment says in collision, so we're going to excise that segment, and then we replan around the broken segment using a standard RRT. Next slide, please. Hopefully this will play. Yeah. So we put this on a real fetch robot. And next slide. Dirty laundry. First is that the speed of ClearanceNet sometimes fluctuates based on unpredictable changes to the TensorFlow code base. And the second one is that we don't have any sensing in our pipeline. And so when recording videos on the real robot, I had to very carefully match the real world state to the state in the simulation, which is not ideal. Happy to take any questions.
Oh, perfect. Yeah. Questions? Yep.
Yeah, I have a question. Yeah, thanks for the great talk. one question I had was that in the paper, and you briefly alluded to it here, you described like a gradient repair procedure that you use, like where you use a gradient of the learned collision checker to like update plans when your like geometric collision checker indicates that you're in collision. I was wondering, I guess like the interesting thing here is you're using the gradient of your collision checker, of your learned collision checker to update plans in regions where your learned collision checker was incorrect. So I was wondering like how often you find that, like how often this procedure works in practice, because I could assume that maybe one concern could be that like in situations where, you know, your clearance net is incorrect, maybe the gradients would be less accurate, or do you not find that to be the case?
Yeah, thank you for the question. That is a good point. In practice, we find that sometimes it works and sometimes it doesn't. You know, there are definitely situations where the like clearance net knows which direction is more into free space, but it doesn't have the boundary between collision and no collision quite right. And so in those cases, using the gradient is helpful. But then there are also going to be some situations where it's just completely inaccurate, and then we have to fall back to excising broken segments.
I see. So could you imagine like rerunning clearance net with like a larger threshold in these cases as well? Or do you think that would do similarly to the gradient repair procedure? Or do you think there'd be more of a benefit from the gradient repair procedure?
Yeah, and so one of the modifications that I skipped over in the interest of time is that we actually have a variable thresholds. And so we start out at around 0, saying that 0 clearance is the boundary between collision and no collision. And if that doesn't work, then we relax the boundary and we allow some more potentially in collision samples to be used. Yeah, so we do incorporate that into our RRT.
All right, thanks
thank
very
you.
much. Thank you both. All right, Terry, take us to the home stretch here.
Okay, hello, last presentation. So the problem I'm trying to solve here is you have a bunch of carrot pieces that are finely chopped, and you're trying to find a sequence of pushes to trap all these pieces to a target set. And the reason why it's interesting is because it's almost impossible to solve this in model-based problems. You cannot estimate every state of carrot particles and everything. So we're trying to solve this problem from evolution of images perspective, like visual foresight. Next slide, please. So the first thing we did was come up with the control Lyapunov function. All that is just a bowl-like function. When multiplied with the image, gives you some notion of the energy of the system. And this tells you this is the correct controller if you have the right model. So if you greedily decrease down this energy landscape, you will stabilize the target set. So the core question is how to model how images evolve over time. And the deep visual foresight from Berkeley folks, I think it's one solution that everyone likes to throw. And the second one we tried is the switched linear model, where the evolution is modeled by linear multiplication. Next slide, please. So it turns out, in terms of the prediction image, they look approximately similar. Sorry, just waiting for the video to load there. I was hoping they would sync up. But let's see. On simulation, when you couple that with the closed loop policy, you can see that the linear model is doing well. The deep visual foresight, DVF, does well with data augmentation. But without data augmentation, it fails. So it's visually plausible, but it still fails. Next slide, please.
Sorry, I'm trying. Oh, there we go. Okay.
Okay. So if we put this on a real robot, we actually see that. Oh my God, the sound. The linear model is able to do this really well. The original fails as expected, but the AFI model, which used to succeed in simulation, is now failing, which clearly states that deep models are overfitting to the simulator environment. So for this problem, at least, it seems to be the case that linear models have amazing inductive bias. Next slide, please. So the key lesson here is that when we model evolution of images and visual foresight, we're too keen to go over to deep models too fast. It's just a video of spelling MIT. It's a fun video. But the dirty laundry we found later on is really this model only sometimes. So this linear model doesn't generalize to rigid objects or more dynamic problems that are not quasi-static. All right, that's it.
All right. Chase, you have a question?
Yeah, thank you for the talk. I really love the problem setup. I'm curious, you said that the linear models work really well for caret herding, but not so well for rigid bodies, dynamic problems. I'm wondering if you have an idea of where the boundary is, where the linear models start to fail, or what is it about caret herding that makes it so good for linear models?
Cool. So there's like two insights here. One is like think about the whole pixel space as an MDP, where every state is a pixel. Every pixel is state. And the evolution of MDPs, their distributions, so they're always linear. And it's called the Permute operator in a more mathy sense, but basically it's the evolution of densities that are always linear. And if you do a finite approximation of that infinite dimensional space, it's still pretty linear. So the key point here is there has to be no coupling between each caret particle. So it models a distribution, and that's why it's linear, and that's the assumption that makes it linear. Yeah.
Got it. Thank you.
Terry, have you tried here something, more classical, segmentation of, the things you see relative to the clean background and the linear motions for pushing from the sides until things converge to the center? And how does this fail relative to the deep network?
I'm sorry, what did you exactly mean by segmentation? Is it like
like 10, 20 years ago, right? You would segment the objects, and then you would try perhaps to define manual primitives of going from the sides towards the center and pushing along desired directions.
I see. This problem does admit like those kind of simple policies, I think. We haven't quite tried the segmenting approach. One thing we have tried is think about the segment as a particle, like think in the Lagrangian space of things where particles are actually moving. And that actually succeeds pretty well too. So yeah, I'm not sure if that answered your question, but I believe there's a solution that goes along that route as well.
Okay, thank you.
I had a quick question. Yeah, like really cool videos, right? So the problem is really interesting. So I was wondering, like, is your current like training or modeling sensitive to the actual dimensions of the brush or the pushing thing? Like, will it change if you have a much wider brush which lets you push all of them at the same time, maybe?
That's a really good question. I think it is. And especially as your pusher width gets smaller, then you find that the energy function we've defined, like the control Optimal function we had, there is no way to decrease the energy of the system if you have like a really small pusher. So I mean, it's definitely sensitive there. It has to be within some reasonable range of things, but we haven't quite looked at like the rate of descent or something like this yet.
Okay, thanks, Terry. Let me just, we did skip a talk. So I've been keeping my eye on the participants, and I haven't seen either Zach or Jan anywhere, but maybe they've got a different login. I just want to circle back and see if we have one of the authors from that talk.